We have some small parts at the end of this chapter you should be aware of. Something that is called Thevenin and Norton source equivalence. And the reason that we are doing this is as follows. When you have an effort source or a flow source attacking a big problem, then you may use causal strokes and then easily find the state equations. An effort source, the causal stroke has to be here. Flow source, it has to be here. But when you have a real source attacking a problem, then you can't really do this. Then you can't use causal stroke at all. Then you have to find the equations by the long way. Set up all algebraic and differential equations and do the algebra yourself. So it would be very, very nice to have either effort or flow source. We don't really like the real sources. Here we have a trick to make our real sources to something that can either be an effort or a flow source. And it's called the Thevenin and Norton. So if we start with a Thevenin source, Thevenin, a source equivalence. So here with an effort flow diagram, effort and flow, you have some real source. So the characteristics of the source shouldn't be too complex. If you remember exercise 2, where we had the motor, it went something like this. Not so easy to model that one. So if you have a linear connection, that's much easier. It can be modeled with a nonlinear, but let's start with the linear characteristics. So this is from the real source. Here you have a real source, real S. This I don't like. I won't have it because then I'm down here. I can't start with the causal strokes. But with Thevenin, I will transfer this behavior into the following. I will have an effort source, perfect effort source. Then I have to look at this point here and say this is my ideal source. So here I have an S effort, but I don't really get the behavior I would like to have. So what do I have to do? Well, I have to take a minus, and then I need something like this. If you subtract these two, then you will get the behavior we are interested in. And here, both these diagrams, of course, with the effort and flow diagram. Effort and flow diagram. Now what is this? Here, something linear, proportional, I mean the effort is proportional to the flow. Ah, this is a resistance. There we have the connection, effort proportional to the flow directly. So we can then do the following for a Thevenin source. So this is actually what we have, source, real source attacking something. Now I will have an effort source, ideal effort source, constant effort, and say the point here is then given as say effort 0 here, effort 0, effort 0. Then I will have a subtraction. Okay, then I will use a one junction down here to this resistance, and then I continue. Well, a one junction, that's common flow, but I have to take the summation rule for the efforts. The efforts should sum to 0 here. So what comes in equals what goes out. And here, what's the effort here? If we have a flow, well, the effort here, effort from the resistance equals R times the flow. And what do I get up here? Well, I will have an effort 0 minus this effort R, or minus R times F, if you like. So there you have it. You just have to design your resistance to get the correct slope. No problem. And as it is indicated here in the book, you may even want to, if the real characteristics is not a straight line, it is maybe curved or it's a function, yada yada yada. Okay, then this resistance is not constant anymore. Then he also is a function. But we can still do the same thing. That's important. That's the whole point. And now you see from this problem, my real source attacking something. This something will be here. I don't know what this something is, but at least now I can start. It's an effort source. Causal stroke goes here. Absolutely. And then I have begun using the causal stroke. Much easier to find the state equations. That's the philosophy. Questions to that one? I'll give you an example afterwards. That was Thevenin, Norton. You will use a flow source instead. So you have the same problem, but now we are focusing on this point, F0 or Q dot 0 if you like. So I want to obtain this, start with a linear behavior with a flow source, an ideal flow source. And for an ideal flow source, well, he will provide that flow regardless how heavy it is. So he will just look something like this. Here you have an ideal flow source. And then again we need negative. We have to subtract, and it will be just equal to the last time. You're going to need resistance to subtract. But now maybe easier if you had drawn these diagrams flipped. So as a flow as a function of effort, maybe easier to see that the subtraction here will give this picture. So normally you are not sort of used to a function that has infinite numbers of answers to one argument. So it's better maybe to flip it. Then it will look identical to the Thevenin equivalence. But the answer will be identical. But here, to obtain a source, so now you have a flow source hitting, and what should it be? On the other side here, you will now have a difference in flow. Then you use the common effort junction to describe this. So here you will have your F0, and it's a common effort. So if you know the effort, say here's just an E, then you can find the flow here. Flow from the resistance, that will be this effort divided by the resistance. And then summation around a common effort junction. The flow goes that goes in and equals what goes out. Hence the flow here will be F0 minus this FR, which then should mimic this one. And then comes the rest of your system. So again, we have gone from this description to now this one. Flow source, causal stroke has to start there. And then you can continue for the rest of the system with the causal strokes. Any questions to that one? Also, this one, of course, doesn't have to be a straight line, can be more or less a complex function. Then this resistance here is not constant, has to be the same function to get the correct behavior. So let us take a quick example. I have a real source. Say this is the rotational world, so I have torque, rotational speed, m and phi dot, as we had in exercise 2. And I say I have a linear connection here. So m equals m0, that's this value. And then minus, I will then have phi dot multiplied with, say this value here is phi dot 0. Then we have to multiply with m0 divided by phi dot 0. So that one should be correct. If phi dot is 0, the torque is m0. If phi dot equals phi dot 0, you will have 0 torque. So there you have a linear connection. M as a function of rotational speed. So this is what I've got from the shop. The problem is then my source. Say a motor of some kind, including the battery. So here I have the source, and here I have a heavy flywheel that rotates, and then I have a rotational dashpot attached to a solid wall. So this one, inertance, here, and R. So this is my problem. And you switch on the motor, the source, the flywheel will start to rotate, and it will spin up until the speed gets so big that you have everything in balance. So he should level off at a steady state rotation, depending on the resistance, of course. So what will the bond graph look like? You have a real source. So you start with an S. Then you will have one junction. You have some object here with its own unique rotational velocity. And this rotational part has mass. So the inertance goes there. Continuing, I hit a resistance. A resistance we insert with a 0 junction. You have the same torque on each side of him. So here are resistance, and then we continue into another one junction. That's a solid wall. He is not rotating at all. Phi dot is 0. So there you have the raw bond graph. And now simplify. 0 rotation. Okay, you have some torque attacking the wall, but he's not rotating. 0 power. We remove this bond with no power. Then this 0 junction can be removed. It has only 2 bonds. So away with him. And then we are left with S hitting a 1 junction where we have an I and an R. That's it. That's all we have. And now we can go no further using bond graph directly. We can't use these causal strokes because this is a real source. So here, what should we do? Well, we have no option. We have to do the algebra ourselves. Okay, here I have one equation describing the source. That's one equation. I will have another equation from the inertance, the I element. There we know the coupling. We have, say, some rotational speed here for this one junction, phi dot, which is of course unknown. So if we know the speed, how did I do this? I did it this way, okay. Here you have an effort source equal the torque. Here you have an effort for the inertance. What's the effort for the inertance? Say you know the speed. How can you find the effort for the inertance? What was the rule for an inertance? Well, we would like to have the following. Effort equals P dot. And down here we would like the flow to be P over I. That was the flow, or Q dot if you like. Now I go the other way around. I know the flow. What is this one? Well, you have a P here. You have to multiply the flow with an I and then take the derivative. So this will be ddt of the flow multiplied with I. So for the I inertance, the effort I equals ddt of the flow phi dot multiplied with I. For the resistance, what do we have there? Okay, say we know the flow, then the effort from the resistance equals the flow multiplied with R. So here I have equation number 1, equation 2, equation 3. What about the last equation? Do we need one more? How many unknowns do we have? Unknowns? Well, for this problem I have 1, 2, 3 efforts. 3 efforts and the flow. 3 efforts and 1 flow. So I have 4 unknowns. I need 4 equations. I'm missing 1 equation. Which one? Sorry, what?
The efforts in the joint.
Yes. The summation rule around the one junction. So effort in, effort S has to be equal effort out. Effort R. That is equation number 4. There you have it. So if you want to solve this, the effort S equals, and then start inserting here effort for the inertance. That should now be the time derivative of this one. Well, that will be phi double dot I plus, and then we have phi dot resistance, like that. And this one equals the effort source, which is equation number 1. So this then should be m0 minus phi dot m0 over phi dot 0. So here you have the entire equation, now written as a second order equation. Then we have to split it up, rewrite it as a set of first order differential equations. Yes, you can do this, it's possible. And of course, for such a simple problem like this, no biggie. Of course you can do this. Now, do the same, but do it with a Thevenin source. Thevenin source. Well, Thevenin, that was an effort source. And then a one junction down to a well-designed resistance. That one has to be found. And then on the other side here, I will then have the real source, should be here. And what do we have for the rest of our system? Well, that is the same as we have here. One junction and then an I and an R. I and here an R element. So actually I get two one junctions next to each other, which of course can be joined if you like, no problem. Before we do that, let us just check that we have done this one correctly. So here I have M0, this constant torque attacking the system. But then I want minus something. So what must the resistance be? Say you have some rotational speed here. Then you know the effort here. Effort from the resistance equals R times phi dot. And here I will now have M0 minus this R times phi dot. Okay, compared with equation 1 over there, this means that this R here, he must be equal to what? M0 over phi dot 0. M0 over phi dot 0. If you choose the resistance like that, then you will have the equivalent Thevenin source. Finished with that, you can join these two together and simplify even further. Effort source attacking a one junction with a mass, and you have two resistances. Now we better separate them. This is resistance Thevenin, and here I will now have a common resistance, an equivalent resistance covering both of them. So he will now read RT plus R. There we have it. Let's see, where are we? There we are. Can we move this one? And this one we don't need. And this one we don't need. So here I have now a constant source, ideal source, effort source. What about causality here? Well, you start always with the sources. So the causality has to be towards the one junction. What was the rule for one junction? You should have all strokes towards him except one. Well, now I have a choice, but I have an inertance, so I choose the integral causality. Then the last one is given. Has to be like this. And you see it's a causal first order system. Everything is A-OK. So here you would now write P dot circle, and on the other side P over I, instantly. Next, you ask the one junction there, who is deciding the velocity? Who is deciding the flow? That's where you're missing a stroke. Okay, so this P over I flow, he's the one in charge. So the flow equals P over I, even here as well, but for the sources they are seldom interesting, so we skip that one. But then we know the effort here. I will have an effort equals R marked multiplied with P divided by I. Okay, now the bond graph is fully annotated. All bonds has two elements, the flow and the effort. And we find the equation by the summation rule. And here the summation will be for the efforts around a one junction. The sum of the efforts has to be 0. So whatever comes in equals what goes out. And out we have P dot plus, and then I have R marked multiplied with P over I. P over I. So this is what I get. Doesn't look exactly the same, does it? Let's have a look. I rewrite the equation. P dot equal M0. Then I will have minus this R marked. What was him? He was this Thevenin resistance, which we defined as M0 over phi dot 0. That was him, which was given here, plus R, plus an R, and this one multiplied then with P over I. Still doesn't look identical, does it? Well, but remember, what is P over I? Well, that's the flow. So you can substitute P over I with a phi dot. Okay, phi dot. Then what's this? Well, P dot, this one, then has to be equal, what will it be? An I and an phi double dot. Then you see we have the same equation. I hope. Minus, minus, plus. Yeah, I believe it's correct. So, okay, for this simple example, I don't know which is the easiest, but trust me, with more complex bond graphs, finding the equation with all the algebra can be very heavy. You can have quite a big amount of equations you have to play around with. Some will be differential, some will be algebraic. It can be a lot of work. But using the causalities, much easier. Much easier. Any questions to this example? That's okay. Truncation of transformers and gyrators. Here we have a very nice little list, and this one you will find this one on the attachment to the exam, so you don't have to remember this one. But you risk on the exam, I will ask you, show one of these. How can you find it? How can you prove it? I mean, we used one for the exercise 2, but there it was just given to you like sort of a rabbit out of a hat, no proof. So let's test these equivalences. So how should you test it? How should you check this? And let's start then with the one that we used. That was a transformer hitting an inertance. And then I said this is the same as something hitting an marked inertance, equal to transformer square multiplied with the inertance, the original inertance. How can this be true? If you want to check this, you have to do it, or you should actually do it 2 times. Say, start with the causality that we would like to have for an inertance. Start with the integral causality. How was it then? Well, for the inertance, I want the causal stroke to be towards the inertance, like that. A transformer, he doesn't change the order of the causal strokes, hence it has to be like this. And now say you know the flow. You can start here with flow. And here you start then, or you have an effort. When you have the causality like this, then it is the effort hitting now the transformer, always the effort towards the strokes. So what will the effort be on the other side? That was the definition of a transformer. That was 1 over T times this effort. And there, this 1 over T effort, this is now what we called a P dot. And for an inertance, what you get down here, you will have P divided by I. That will be your flow. What will he be? The P over I? Well, that will actually now be the time integral, or whatever you have here. Time integral of effort divided by T dt, and then divided by I. This is what you get here. Then finally, what will the flow be on this side? Well, the flow here, he will then be, and again the definition for a transformer, it will be 1 over T multiplied with the flow on this side. It will be 1 over T multiplied with P over I. And where P over I is this time integral thing, if you want to insert it. Normally you don't have to here. So what will then be the equivalence? Well, you send in an effort and you get back a flow. And you get back a flow looking a little bit strange, doesn't it? Let's see. You send in an effort this way, and you get back a flow, and the flow, he looks like your original effort. You insert it here. Say the T is constant, then he can go outside. it will be 1 over t square time integral of effort by E dt. What is this? Well, this is exactly what you would have gotten if you had an inertance here, goes to stroke like this, and you have to then call him something else than the one you have here, because you have gotten the ratio t square in addition. So this inertance will then be 1 over E times t square, hence you have it t square multiplied with E. So that was with the integral causality. Then you can do it once more with differential. And I think actually that one will be a little bit easier, won't it? Yeah, never mind that. We can easily try it here. You do it like this. Now it is the flow that's going to the right. Here you have a flow. What do you get on the other side? Flow times transformer. That's the definition of a transformer. Then we have to go sort of the wrong way. Now we have a differential causality here. So instead of this definition, P dot goes to P over I on the other side. We have to think differently. I have the flow. How to find this one? Well, you take the flow, you multiply with I, and take the derivative. So here, time derivative of the flow, ft, and then multiplied with I, like that. Then we have an effort here. What will be the final effort here to the left? Again, definition for a transformer. That will be T now multiplied with all this. And here, transformer constant goes outside, I constant, and finally derivative of the flow. Well, I'll just yeah, I can write it like this, dt over flow. And again, yes, you get t square times an inertance. T square times an inertance, which is then what we have here. So you just try it out both ways, then you are certain. It would actually be enough with one to prove it. The other one can be sort of shown the exact same way. The gyrators are a little strange. Here you have a gyrator and an inertance. The equivalent there will be a spring. So a mass goes to a spring, and also vice versa. Gyrator hitting together with a spring, the equivalence is a mass. Quite strange actually, but if you look into it, this is what you get. Okay, that was the equivalences. I will continue here then tomorrow. We are missing the mesh reduction, and also I will have a peek into chapter 6. Any questions? And we stop here.